Yeah, so good to have you all again in this class. So,
Morning, sir.
yeah, good morning, a very good morning, everyone. I I was able to look through your submissions, so we are going to be going straight into your presentations, okay? But before we do that, I realized a few gaps. So I'll try to bridge those gaps right away. Then while I do that, I would love group two to get ready for their presentation. Is that okay? Is that okay, please? I need your feedback.
Yes, sir.
Okay, that sounds good. Okay, so going by the previous curriculum before the modifications we made, we're as good, as done with the lecture, with the course, okay? Because we've literally covered, the major details, okay, in the course. But we'll try as much as we can to keep up with our activities. And next week, we won't be having a regular Zoom lecture. So we'll be migrating to LMS, where we'll be taking a little in-class exercise. So the class time will still be the same, okay? So you'll be expected to engage the LMS and then attempt the problems that will be posed within the class duration, okay? And we'll be expecting your feedback on or before the class time is over or the scheduled time is over. I hope that is clear. Is that clear, please?
Yes, yes, sir.
Okay. Okay, that sounds good. Okay, so okay, go ahead, please, Jeremiah.
Yes, sir. Are we also going to be, since we're having a test next week, are we going to have to submit a presentation slide for next week as well?
Why not? We are going to submit that, only that the presentation slide, we are going to make the presentation, we may make the presentation alongside, but what we mapped for next week is the class exercise. So if the class exercise is going to take less than 2 hours, then we may migrate to the Zoom platform for your regular presentation. Notwithstanding, you have to get your presentations ready. Is that okay?
Yes, sir. Thank you, sir.
Yeah, so get your presentations ready. Then, depending on the duration for the class quiz, then if we still have some time, then we could make make our presentation. But if not, then we move it up to the upper week. And then we may be having a crash through exercise where we may have to combine both weeks. Is that okay?
Yes, sir.
Yes, sir.
Okay. Now, this is sequential logic and finite state machines. And this is about what we've been playing with for a very long time. So before I move on, I wanted to tell me what sequential logic means. So you can unmute and let's get talking. When we say sequential logic, what do we mean?
Good morning, sir.
Very good morning.
So, sequential logic is a logic circuit that has memory, unlike the combinational circuits.
Oh, okay. Sequential logic is what?
a logic circuit that with memory. So
And you said it could also be what?
it is unlike the combinational memory.
Okay, it is unlike. Okay, that's the word I wanted to get. It is unlike. Okay, so we know the combinational logic or circuit does not include memory. So what defines that memory in the sequential logic?
So I think
Like
it's
it's
the past
Okay,
past input.
okay,
The past input define the memory.
okay, the past input. So now I wanted to make a little reflection on your signals and systems and then come back to this, right? So if we say the past input, so which of the devices can we use to represent this past input or memory?
Flip-flops.
Flip-flops. Only flip-flops?
registers. Sir.
Okay.
Okay, is that all?
Latches.
You can use FSMs too, sir.
Yeah, latches. Yeah, we can also use latches. Yeah. Okay, so that's pretty cool. So fine. So I really do not have much to say. So we'll just dive right into this. Okay, let's annotate this then. Okay, so you already mentioned that a sequential logic, talk about sequential logic. You just said, well, it contains a combinational circuit for which we can take in certain inputs. Okay, so let's say this is X1, S2, all the way to Sn, and at the same time have some outputs all the way to Y1, Y2, all the way to Yn. So that's a combinational circuit. But the point is, okay, let us extend this. Let's extend this. Okay. Now, for us to have a sequential circuit, then it means we have to have an input to the memory, right? And we'll call that the excitation. So we have the input variables here. We also have the output variables here. And then for us to have our past input values, so we have to introduce a feedback, okay? For which this is now the flip-flop, right? And this feedback, this link initiates the input to the memory, right? This is input to the memory. And we'll call this the excitation variable. So we now have this. So it could be multiple. We could have more than one of these all the way. So we have the flip-flop here. So at this point, we have the output. This is the output of the memory. And we'll call it the state variable. Okay. So perfect. So this is what we have, okay, for the flip-flop. And we know that we have variants of flip-flops. So who can tell us, the types of flip-flops we have? We are just trying to revise what you already know. So I need the
I
class.
think we have
Go ahead.
D flip-flop, JK, RS.
So you said we have the what? You said
D
the
flip-flop,
RS, D flip-flop, what again?
JK.
JK, and what again?
I think we also have the T.
Okay, the T. So, well, these are some types of flip-flops, right? So let's just put it FF, right? Flip-flops. And how do we characterize these flip-flops? So what are the major metrics to look out for when characterizing the flip-flops? Who can help us, please? The major metrics. So how do we tell the difference between, what are the metrics that can be used to distinguish between the ROS or SR, D, JK, and T flip-flop? What are the metrics?
The excitation table and the characteristics table.
Okay, so we'll talk about the excitation table, the characteristic table, right? And we can also talk about one more thing beyond that. You mentioned the excitation table, the characteristic table, then there's one more thing. Talk about excitation table. And we'll talk about the characteristic table. And what again?
Timing diagram.
The what?
Timing diagram.
Okay, timing diagram. Okay, fine. There's one more thing I want to hear, timing diagram. And
The
what
state table.
The state table. Okay, I think that we can link that to the characteristic table, right? Set state table. So state table. Then there's one more thing. So who can help us? One more thing. Yeah, excitation table, characteristic table. Yeah, we can link this to the state table. Yeah. Because with the state table, we can begin to draw lines to tell the states, all of those, blah, blah, right? Right? Things like that. Okay. So then what else? What else? What else? I need someone to tell us. Okay, so we just mentioned it, so we don't take too much of our time. The characteristic equation, right? Now, do you know how we could, okay, let's put it this way. How do we derive the characteristic equation? How do we derive this, the characteristic equation? Ayobami Faith, can you
I
help?
think one of the ways you can go about this is by drawing the equivalent logic circuit of the
Okay.
flip-flops and then applying input to see how the output is going to change in response to the input provided.
Okay, one way to derive the characteristic equation, right? That's okay. And one simplified way too is to use the Kanoff map, right? And the Kanoff map will be derived from the characteristic table, right? Isn't it? Okay. Now, well, these are things you already know. I just want to throw in a little detail so that we are able to move on. So we already know that the flip-flop usually include the input, right? So it could also include the clock, then the initial state and the final state. So Q, T plus 1, the final initial state, final state. Then here we have the clock signal, right? Going into this part. So usually flip-flops are designed this way. So should we have either ROS or JK? So this could be R, then, or better note, this could be set, reset. Let's put it that way. Set, reset. It could also be JK. Then in the event that it is D or T, so we do not have this, it's just either D or T, right? Okay. So more like the pictorial view. And one interesting detail about the flip-flop is that it's able to store 1 bit in memory, right? So as such, we have all of these, well, I'd rather say SR flip-flop. Okay, then we can characterize, or better still, having all of these, then we should also have the clock signal, and then we should have the state, right? So the components this time. So we have the input, we have the clock, then we have the state, the initial and the next state. Is that clear, please?
Yes, sir.
Okay. Now, before we delve into the characteristic table and these characteristic equations, now we have how many types of sequential circuits? How many types do we have? Who can help us with this? Types of sequential circuit. Can Jeremiah help us? Jeremiah Ogunfuwa. Can you help us with this?
Bistable circuits.
What's that? I mean, sequential, right? Okay, so I'll just move on. We have synchronous sequential circuits and also asynchronous sequential circuits, okay? So for the synchronous, then we need a clock, okay? So for synchronous sequential circuits, when all state changes occur at clock transition or the clock signal transition. So here we need a clock for clock transition, but for asynchronous, it's such that all state change occurs immediately after the input change without a clock signal, okay? And now that we have to play with the clock signal, so let's move way into flip-flops. So we have SR flip-flop, and the design looks something like this. It's S, set, reset, and this is the clock signal. Then we have Q and QT plus 1, okay? And if we have the present state where Q, let's change the color. This is set, this is reset. Now this is the clock. This is present state. Then this is the next state after transition, okay? Then let's assume we have let us consider 8-bit sequence, for instance, or 8-bit combination, where we have the present state to take on values, say 4 zeros and 4 ones, right? Then the SR input, the set reset input, can take on values 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. So what is going to be the next state? QT plus 1. So I want us to do this together. Okay? Well, this is what you already know. We just want to revise. So we are sure specific details are covered. Okay. Now, when the initial state is 0, and then the set, we have the signal set to 0, and the reset is also 0. So what is going to be the next state? Who can help us with this? Any feedback, please?
0.
Is 0. So how did you get that? So the next question that comes to mind is how? How is it 0?
So I think we would have to derive the characteristic equation first.
Okay, so, well, I'll just give you the rule of thumb. Okay, so when the set, oh no. When the set is the same as the reset and is 0, then the initial state and the next state are the same. Okay? And when the set is the same as reset and is the same as 1, then the next state, which is qt plus 1, is invalid. Okay? And when set is the same as 1, then the flip-flop sets to 1. And when it's also 0, the flip-flop sets to 0. Okay? And when we have the reset taking on value of 1, then the application of the clock pulse resets the flip-flop. Okay? Okay, so now when the set and the reset are the same as 0, like we have here, we have 0. So we also have this, but you realize that the initial state is 1. But the fact that the initial state is 1, and then we have our set and reset being 0, then what is going to be the value?
1.
Because the initial state is 1, right? So here the initial state is 0. So once the set and reset is 0, then the next state is 0. Since the initial state is 1, once set and reset is 0, then the next state will be the same as the initial state. Perfect. Now, regardless of the state, the initial state, when S and R happen to be 1, then the next state will be what? Invalid, right? So this is going to be, let's put X invalid, okay? So this will be X, this will be invalid. Is that clear? Huh? So when set is 0 and reset is 1, what do we have?
0.
0, good. And this case, set is 1, so what do we have? 1. Okay, set is 0, this will be what? What's going to be the next state?
0.
0, because set is 0. And now the next state here, the next state is going to be what this time?
1.
1. Perfect. So we have the characteristic table, right? This is the characteristic table. So what is now we're going to derive the characteristic equation from this model. And well, we said we could use K-map, right? So from K-map, we have Q being the state slash SR. So our possible combination is 0, 0. Then we have 0, 1. We have 1, 1, 1, 0. So this is more like saying S bar, R bar. Then this would be S bar, R. So this would be SR. Then this would be SR bar, right? So here we have 0, 1, meaning Q bar, Q, right? For the K-map, isn't it? Is that clear? Is this clear, please?
No, sir. Come again, sir.
No, sir.
So we are just drawing our K-map, our regular K-map. So your regular K-map for 1, 2, 3, 4, 5, 6, 7, 8 logic lines for your truth table. Recall that. So we have this. This is just the table this time. So it's we are plotting Q slash SR. So where the combination here, you know, in K-map we use ABC, right? So we are using SRQ this time against ABC. Is that okay?
Yes, sir.
Yeah, so we have S bar, R bar, S bar, R, SR, SR bar, then Q bar, Q, right? So where we have C bar, C, then A bar, B bar, A bar, B, AB, then this would be AB bar. You get it, it's just a table for the K-map, right? So we want to now plot what we have here. Okay, now the final state in this case is 1, so we can plot this. So we can plot now. Okay, let's change that color. So now we want to plot on K-map. So we won't be able to plot this because it's not on. This is not on. This is not on, right? So, but this is 1. This is invalid. This is 1. This is 1. This is invalid. So we can plot all of those. So we can plot this when we have, this is S arrow bar. That's S arrow bar, right? That's 1, 0, 1, 0. But this is when we have Q bar, because all of this means Q bar, while all of this is Q, because Q is on here and Q is the complement here. Is that okay?
No, sir.
Yeah,
You said it's because Q is the...
No, this is, now these are the values of Q. So when Q is 1, so it means Q is active, right? It's
Yes, sir.
yeah,
It's
so
active.
when it's inactive, we say that's the complement of Q, right? When it is 0.
Yes, sir.
Exactly. So that's what it is. So now at this point where we have an active state, active next state, because it is 1. Now SR is 1, 0. Then it is Q bar, right? The initial state is Q bar, is 0. So where are we going to plot that? We're going to plot that here. This is 1, right? So we have plotted this. SR is 1, 0, which is the same as SR bar, right? And we can plot that on this row, which is Q bar, for which Q bar is 0, right? So we've plotted that. We have an on state, next state, right? Because we want to find the state equation for QT plus 1 is equal to what, right? So we only check out where the next state is available, whether it is valid or invalid, right? Now, at this point, it is available, but it is invalid. That is 1, 1, right? So we just put the X there. It's invalid, right, for this. So it's still on Q bar, right? So we have also plotted this, right? Now, the next now is for Q. 0, 0 it is on, right? So this is 1. That's for this, right? 0, 0, S arrow is 0, 0. That's X arrow, S bar, arrow bar. Is that clear? And Q is active. Q. Yeah, so that's that. So this is now then, when we have 1, 0, 1, so this is also active. Then when we have 1, 1, then this is also active. So we can do our grouping, right? So let's change this color. So we can group 4s. We can equally group 2s. So let's change the color. We can group 2s, this and this. We can group 8. Recall your algorithm for K-map, right? So when we group for 4, what are we going to have? So in this case, arrow and arrow complement, which will cancel out. So we have S, right? So what we have is S. Then on this part, Q bar and Q will cancel out. So this is S, right? Now for this folded part, we have, okay, S bar, S will cancel out. So we have arrow bar, right? Arrow bar is active. Then what do we have? Q, right? So that the state equation will now be
Sorry, sir. I didn't get that, sir.
S plus arrow bar Q. Okay, recall your K-map, right? When we play with K-map, I think we had that we walked through K-maps in our last class, right?
Yes,
Okay, then we have some examples in our previous videos. Now, this is the folded part, this and this, right?
yes, sir.
Now, so we are going to be considering this, this,
And that.
and this, right? So this is common. It does not have its complement, so it's going to remain, right? That is the Q. Now, in this case, S bar and S bar is the complement of S. So they'll cancel out, right?
Okay.
So what we have left is arrow bar, which is common to both, okay? So that remains.
R bar Q.
So that becomes arrow bar Q. Why this? We already worked this out. Q bar Q is going to cancel out, so Q is not going to be selected in this K-map algorithm. Then we have S is common, but we have arrow bar will cancel out. So that's why we have just S, right? So the characteristic equation becomes S plus S bar Q. Okay, so this becomes the characteristic equation. I think that's clear, okay? For the SR flip-flop, okay?
So can the characteristic equation be derived without the characteristic table?
We'll definitely need the characteristic table to derive the equation. Just take note, this is characteristic table, so this is characteristic equation.
Good morning, sir.
Very good morning.
Sorry, sir, I have a question.
Go ahead, please.
Okay, sir. According to some textbooks, the characteristic equation can be gotten from the flip-flop or latch logical circuit. So is it that sometimes you do not need the characteristics table to get the equations?
Okay, so probably what we're going to do now, probably we'll pose one more, we'll look at another flip-flop, then we'll leave that to you to use the circuit to derive the equation, then we'll now compare with our characteristic table. Would that be fine?
Okay.
Or you don't want to go through that trouble right now?
It's no trouble, sir. It's no trouble.
Okay, but whichever way, I don't think that's any trouble, you know. Yeah, because the characteristic table is typical of the circuitry. Okay, this is
Okay, sir.
just the logic representation of the circuit itself. So this is what is implemented. Okay, so whether we now decide to play with the circuit or not, it's all the same. We are going to get the same outcome. So probably you want to play with that to see if you'll get what we got for the characteristic equation. But this is just a simple, straightforward approach, okay? Is that okay?
Yes, sir.
Okay, now that we've done this, I want to believe you should be able to walk through your D flip-flop, JK, and T flip-flop. Or do you still want us to look through them using the same approach?
Yes, sir. Let's look
Yes,
through
sir.
them.
Yes, sir.
We should look through them still.
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Okay, I was thinking we just move on then. Okay, fine. Let's look up another one then. So let's take your D flip-flop, for instance. So here we already know that you call this the data flip-flop, right? So the output follows the input at the clock edge. So what we have as the input D is what we get as our next state. That's the idea. So so we have this. This is what we have for this. So this is the input D, and this is the initial state, and then this is the next state, right? So for the characteristic table, we have the initial state, then we have the input, then we have the next state, okay? So let's say we have a 0, 0, 1, 1. So we have a 0, 1, 0, 1. So going by our description, then this is data flip-flop. We already said that the input, or better still, the output follows directly from the input at the clock edge. So when the input is 0, what do we get for the next state? What do we get for the next state?
0.
What did you say?
0.
Good. So when we have 1 as our input, what do we get for the next state?
1.
1. And when the data input is also 0, is 0 again, what do we get for our next state?
0.
And when the data input is 1, what do we get for our next state?
1.
1. Perfect. So now we can as well draw our K-map. This is pretty simple and straightforward. So we are plotting Q against D, right? So we have 0, 1. We have 0, 1. So this is Q bar, this is Q. So this is D bar, this is D, right? So now what we want to figure out is QT plus 1. So this is active, right? So when the initial state is 0, then D is 1, then our state is 1. So, sorry, this is not D bar. This is D, yeah. So this is 1. And at this point, it's also 1. So we can do our mapping. So the grouping. So the same way, so Q bar Q is going to cancel out. So that won't be present. Then all we have is D, okay? So the characteristic equation is the same as D, okay? So we now see that the final state is completely dependent on the input D and independent of Q, the initial state. Okay? Is this clear?
Yes, sir.
Okay, so let us look up the JK flip-flop, JK flip-flop. So, well, this more like the SR flip-flop. Everything is much the same, except that it eliminates the invalid state, okay? So the invalid state now takes a complement value, okay? So in this, we have, so just recall everything about SR flip-flop. So this is the clock signal.
Including the left hand rule.
What's that?
I said we should remember everything, including the left hand rule. Left thumb
No,
rule.
no, no, no,
Thumb
no.
rule.
I mean, no, no, no. All I said is just remember everything we talked about the SR flip-flop, except for the invalid state. That's what I said, okay? So here, this JK QT plus 1, okay? Okay. Okay, so now we can now populate the characteristic table Q, J, K, Q, T plus 1. Okay, so what are the rules here? So who can help us? I need your feedback.
Sorry, sir.
When S equal to R equal to 0, Q is equal to QT plus 1.
I didn't get that.
When S equal to R equal to 0, Q is equal to QT plus 1.
When what?
S is equal to
No,
R
no,
equal
this is
to 0.
JK. So we can't be talking
We are
S.
using JK, not SR.
This is JK.
And it said we should say the rules for SR, so
Just replace S and R to JK.
okay. Okay, so when J is equal to K equal to 0, Q is equal to QT plus 1.
When J is equal to K is equal to what?
0.
Mm-hmm.
Yeah.
QT
Q equal to
plus
QT plus
1
1.
is equal to Q, right? Okay,
Yes,
perfect.
sir.
Yes, sir.
So what's the next rule? What's the
When
next?
J equal to when J equal to when J equal to K equal to 1.
Mm-hmm. Then what
For the
happened?
SR, he said QT plus 1 is invalid.
Yes.
But then it will be complements. It will
Yeah,
be
but this
complements.
time it's going to be the complement. So that will be QT plus 1 will be the complement of.
Complement of Q.
Is that okay?
Yes, sir.
Yes, sir.
So every other thing follows directly. Okay. So let us move on. That's 1, 2, 3, 4. 1, 2, 3, 4. That's 1, 2, 1, 2. So let's populate the table. So what's our final state? Final state, please.
Hold on, sir.
So what's the first one? Q.
0.
0. Is it 0? Yes, you're correct. So the next?
0. It's 0.
Then the next?
1. 1.
1. Now, why is this 1? Because of this rule, right?
Because of the complement of
So this
Q.
is not the complement of Q. So 1 is the complement of 0.
Yes.
So then the next?
1.
Good. Then the next?
0.
0.
0. Then the next,
1.
then this,
0.
0.
0, because it's the complement of 1. Yeah.
Q.
So the K map follows directly. So that is Q, JK.
Mhm.
0/JK. So this is 0, 1. That's Q bar Q. Then here we have 0, 0. We have 0,
0,
1, 1,
1, 0,
1, 0.
1, 0.
So this is the same as JK or bar,
JK,
J bar K,
A,
JK,
JK,
JK bar,
AK
right?
bar.
Okay.
Yes, sir. That's K.
So now let us plot this. So we're going to plot just this, and this, right? Because they're active, right? They're in the active state.
Yes, sir.
So for when the state is 0, so 1, 0, so we have this 1, then 1, 1, we have this, then 0, 0, we have this, then 1, 0, we have this, right? That's what.
Yes, sir.
Okay. So now we can do our grouping in tools and this, right? So,
Yes, sir.
so what do we get here?
J,
This is J, right? Because
J, yes,
K bar
because
cancels
K
out.
and K bar
So that's
cancel.
J,
It's J.
J, then we have Q bar is in common, right?
Yes.
Then for this, then what do we have?
K bar.
Now
K
J,
bar.
J cancels out, so we have K bar,
K bar.
K
K
bar,
bar.
Q, all right?
K bar, K bar Q.
So the characteristic equation will now be the same as JQ bar
J Q
plus
bar
K bar,
plus K.
Q.
okay?
JQ bar plus K bar Q.
Okay, so
Yes, sir.
that sounds pretty straightforward, right? So,
Yes, sir.
okay, so hope group 2 is ready for presentation.
So I have a question.
Yes,
Okay,
sir.
go ahead, please.
Okay, sir. Why? Because in the SR flip-flop, we had invalid states.
Mm-hmm.
So if the states are invalid, why are they used in the kernel map?
Okay, now the fact that they are invalid does not mean they are non-existent. Now, how do I place this now? We either have a 1 state or a 2, a 1 or a 0, okay? Now, the fact that it is invalid means that it is unknown. So that is why we placed it as invalid. So when you play with the excitation table, you will now see how we play with that, okay? So I'm leaving that to your presentation because I realized some of you mentioned a few things, but I just wanted to bridge a little gap. Then when we come to questioning, then we'll now establish more details, okay? So that it is invalid does not mean it is not existent. It is only unknown. Is that okay?
Okay, sir.
Okay. Now, just like your D, we have your T flip-flop, right? So let's just do that. Then I'll mention a few things in the finite state machine because I realized that most of you only specified the class A, class B, and class B, but did not specify the class C, class D, and class E finite state machines. And we also need to cover all of those. So that's why I had to do this. My intention was we go straight up into the presentation, okay? But we just need to bridge the gap. Is that okay?
Yes, sir.
Okay. Now we have the T flip-flop. Now I understand you already played with flip-flop in 300 level, right?
No, sir.
Okay. Have you done digital electronics?
Well, we
Yes,
did, sir, but the textbook
it's played it, sir.
What
was
happened?
different. So the textbook, I think, is for master students. It's not easy to understand.
Really?
I mean, not just
That sounds really interesting. Why will you conclude that the textbook was for master students?
No,
So
sir.
are you trying to say your course lecturer decided to use a master student a postgraduate textbook for the undergraduate? And that would have been better, really, because
No, it wasn't.
Sir, how?
that would have exposed you to more knowledge, okay? Anyways, well, I'm sure you had the course curriculum, the handbook, your student handbook at the time, right? So were you able to match what you were taught by your lecturer then with the course curriculum?
We tried our best, sir.
Okay, so I'm sure you were supposed to cover flip-flops, right?
Yeah.
really understand it, sir.
Okay, but do you understand it now?
Yes, it's getting
No,
better.
Okay, so
And sir,
because everything we'll get to
sorry.
do going forward, we'll be playing with flip-flops and and some other combinational circuits, even in error
Yes, sir.
correction. Okay, when we talk about error correction, when we talk about convolutional codes, where you have to play with shift registers, we play with flip-flops. Okay, so that's exactly what we mean. So we try to distinguish between your regular block codes and your convolutional codes. So for your regular block codes, we could achieve them using combinational circuits. But for the convolutional codes for error correction, we now want to implement them using sequential circuits. Okay, so everything you're playing with right now, there are things you get to apply when it comes to modeling and designing, or better say, implementing such ideas. Okay, so you just need to understand the way the logic operates. Okay, so well, unfortunately, this is not a detailed presentation of flip-flops because we just assume, but we just want to cover the peripheral, then move on to implementation. So we just need to know how these flip-flops operate. So when we want to implement a certain idea, we can tell which is appropriate. Is that okay?
yes, sir. Yes. So,
Okay, so we have the T flip-flop where we have the clock signal, and then we have T. So I understand, at that level, you guys must have used the AND NAND gates to implement the flip-flops in terms of the logic gate diagrams, right?
Yes, sir.
Exactly. So you want to see how the sequence flows, but this time I'm using the characteristic table, right? Okay. So the characteristic table is not different from that logic diagram. Okay. So that diagram is a representation, it's typical of this table, right? Yeah. So let's just keep it simple for now. Okay, so we have the initial state and then we have the next state. So we have all of this terminals out. Okay. So the rule of thumb here is that when t is 0, then the next state, qt plus 1, is the same as q. But when t is the same as 1, then the next state is the complement of the initial state. Okay, so let us move on to the characteristic table. So where we have Q, T, and then the next state. So we have 0, 0, 1, 1, 0, 1, 0, 1.
0, 1,
So what's going to be the next state when we have all zeros now?
0.
Yeah, because when T is 0, the next
The
state
next
and the initial state
state
is the same, right? So
is
0. So at
yes,
this point, T is also 0. So what's going to be the next state?
1.
0.
0, 0.
Are you sure?
Yes, is the complement of
No, at this point, I mean,
no,
at this point,
no,
where T is
it's
0.
1. It's 1.
1,
It's
1.
So because
It's
the
1.
next state and the initial state is the same. So this is 1.
Eh,
So at this point, when T is 1, so what is going to be the next state?
Kill the
1.
complement.
It's going to be the complement of the initial state. So the
Complement
complement
of
of
the
0
initial
is
state.
what?
1.
1.
Yeah,
Perfect.
1.
So when T is also 1 at this point, so the next state will be what?
0.
0.
0, because that is the
0.
complement of the initial state. So that is it. So now we can pull up the table, the K-map.
Um,
So we have Q, T. So this is 0, 1. So that is Q bar Q. Then at this point, we also have 0, 1, right? So this is T bar T, right? So we're going to plot just these two because those are the two active states to develop the characteristic equation.
Characteristic equation.
Yeah. So now, when T is 1, what do we have at this point?
1. Hmm?
Yeah, at this point.
1.
Oh, plot 1 here, right? So
Yes.
we have this and we have this. So represent this and this at these levels, right? Okay. Q equal to 1, T is 0. For Q equal to 0, for Q bar equal to 0, T is 1. Okay.
What?
So perfect. So now we know what this is, right? At this point.
Q bar
That's-
T.
Yeah, so that's T Q bar.
Q bar, yeah.
And this will be what?
Is T bar Q.
T bar Q.
Q. So the characteristic equation will now be T Q
T
bar
bar Q.
plus T bar Q.
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 Is that simple?
T
Okay.
bar Q.
So is that simple? And it can be simpler than this. And recall in your okay, no, you haven't taken information theory and coding. There's the idea by the Occam razor. Okay, so you want to figure out what Occam razor means. It's a philosophical concept that says the simplest approach is usually the preferred one. Okay, so we don't want to make life too difficult. So let's always try to figure out the simplest approach to solving our problems. Is that okay? Now, are you still with me? Can you hear me? Oh, I don't know if I lost everyone in the connection.
We can hear you now, sir.
Okay, perfect. So, well, that's a brief recap on sequential logic and flip-flops. So let us quickly revise the finite state machine to cover a few gray areas, then we'll begin our presentation. Finite state machine. So you call this FSM. I don't know why. Well, probably because it's the acronym for this, but FSM could mean something else. Okay. So what is a finite state machine? From your research over the week, what is finite state machine? When we say finite state machine, what does it mean?
Finite state machine is a computational model used to design system with finite number of states and transitions.
Okay, perfect. So you said, now because you brought that word transitions, so it means it cannot be combinational. It has to be sequential, right?
Yes, sir. Yes, sir.
Yes, sir.
Exactly.
Yes, sir.
Now, the fact that it is sequential does not mean that we do not have a combinational component in it, because the sequential logic includes the combinational logic alongside the memory unit, right? But perfect sequential or transitions. So it means that the finite state machine is used to realize sequential logic systems, right? Is that
Yes,
correct?
sir. Yes, sir.
So
That sounds about right, sir.
this is used. That sounds what?
That's about right.
I didn't get that.
It's right. That's right. That's right.
Okay, it's used for the realization of sequential logic. Okay. Now, I wouldn't have done this, but I felt it would be necessary. We try to expand the scope, looking up your submissions. So we have the classification. So now the finite state machines could be classified based on the presence of feedback, the feedback loop, feed forward loop, and some other basic connections. Okay, we'll see that shortly. So we have the class A finite state machine, and you call that the Mealy, right? You guys mentioned Mealy. I saw Mealy in most of your submissions. Then we have the class B finite state machine, and you guys call this the more state machine. Then we also have the class C, the class D, and the class E finite state machines. Okay, finite state machine, finite state machine. Okay. Now, I will not, spend so much time on this, but I will just try to present them diagrammatically. Then we'll move right quick into your presentation, because we need about an hour to do that. Okay, so group 2, please get ready so we do not delay. So for the class A, the bottom line is we have these basic modules, these 3 basic modules. I'm just going to pull them off here. So this is the next state decoder. Then this is the memory. And then this is the output decoder. So we already know that we achieved the memory using flip-flops. Okay, could be quite a number of that. Now the next state is actually realized using combinational circuit, while the output decoder is also achieved or realized using combinational circuit. Okay, now we have the input to the system. This is the input. Then we also have the output. So let's call this Y and let's call this S. Now for the memory, we have the clock, right? And then the input to the memory, we already mentioned that is the excitation variable. So I'll call that EV, right? And then we have the output as the state, which is the present state. I know I mentioned that earlier, present state. So I'll call that P,
Yes, sir.
right? Now we have the feed forward. So the input, we feed it into the output decoder
Output decoder.
as a means of controlling what we receive at the output. And then, let me clean this. I'm going to represent that again. Then the present state is fed back into the next state decoder. So this is the present state, right? And we call this the state variable because it is from the present state. And this is what we call the class A or Mealy state machine. Now, for the class B, we have every other block. So let's put that for class B. Class B, we have every other block, the 3 blocks, okay? But the point is there's no feed forward, okay? So the excitation variable is there, the clock is there, the input is there, then the present state is there, and then the state variable is there, and then we have the output. But you realize that there is no feed forward. So this is a class B. So this is a next state decoder. This is the memory. Then this is the output decoder, right? This is the excitation variable, and this is the present state. So this is the class B, which you call the more state machine. So you now realize that we don't have the feed forward here. So this is the input and this is the output. Why this is the state variable, right? Now for the class C, we now have to retweak a little bit because for the class C, the output decoder is not present. Okay, so we just have the nested variable and the memory. So
the memory.
The output of the flip-flop of the memory is the output, is the final output. So whatsoever we get from the present state becomes the output for the class C. So for the class C, we just have 2 blocks, right? There we have the memory, the next state. Then we have the excitation variable. We have the clock. Then we have the present state, which is our output. Then our feedback goes into this, which is the state variable. And then we have the input. So this is a class C state machine, okay? Okay, now for the class D, there is no feedback, okay? So that we have the same 2 blocks this time, which is the next.
Sorry, sir. Another name for the class C is what?
Well, for now, let's take it as class C. I know Moore and Mealy were named after their inventors, right? Then we have
Yes, sir.
the memory. Then we have, for the class D, we have the present state, which is the output. Then we have the input. Then we have the excitation variable. We have the clock. And then there is no feedback. And this is what we call the class D. And then for the class E, it's just the memory we have, the flip-flop, the flip-flops, okay? So we have the input, X, then we have the clock, then we have the present state being the output. And say this is class E, okay? So that's about it. So I think in most of your presentations, you mentioned class A, class B, but you also need to investigate other classes, okay? And okay, so let us wipe this. So let's see what I have left, okay? Okay, so we have the VHDL code realization for your SR flip-flop, for your D flip-flop. Okay, so we have the D, we have the clock, then we have the output. Then for the JK flip-flop, okay, we have the clock, the reset, the JK, and then for the T flip-flop. And then this is a simple sequence detector finite state machine. So we are meant to detect a sequence, say 111, okay, in a serial port. So we want to identify the states. So here we have state 0, state 1, state 2, state 3, okay? So the 3 states, okay? So in this case, let's say 100, okay? So state 0 is the initial state. Then state 1 will detect 1. State 2 will detect 10. And then state 3 will detect 100. That's just the idea, okay? Or about the sequence detector. So we have a sequence this way. So probably you want to program your bit sequence and all of that, and then you want to use the finite state machine to realize that. So you need to identify the states, okay? So this is one perfect example. So we have the code running. So okay, let us swipe this. And then another one is the vending machine, okay? The vending machine. Okay, so in this case, probably we want to identify that, we have this for vending machine, the clock reset, then the coin, 1 to 0. So in this case, we are using a 2-bit, right? So we are using a 2-bit input to represent either a 0-1 for, say, 5 coin, 0-2 for 10 kobo, then 1-0 for, 10 kobo and all of that. So once we do that, the idea is that you want to program this machine such that once you slot in the required coin, then it's going to probably give you a feedback, maybe the output. They use this in gaming houses. So you go to some of these children gaming centers where you get some coins, you slot it into the particular toy they want to play with, then it becomes active. So you can play with it, okay? So, and it's timed. So once it times out, then you need to get more coins. It's a vending machine. I think you have some of those also on campus. I would know, where you get your coin or your cash, you slot it in, then it gives you the product you want to get, okay? So this is more like the VHDL code to realize that idea. And we have to move between states, right? Between state 0, state 1, state 2, state 3. And once we get to state 3, then it dispenses the particular instruction or ideal product, okay? So this is another simple example of the vending machine. Okay, so I think this is a good place to stop. I think, okay, I have, okay, this is, okay, the last stuff I did here was the vending machine. Where is it? Where is it? Where is it? Okay, so that's it here. Okay. Okay. So, well, okay, good. We have the code running, so that's that. So for the vending machine. So some of these things you could play with and make them little projects. So you want to prepare for things like this in your quiz, so you're able to design and implement an idea, Okay, that's fine. So I think now, let's see, can participants share?
So you said we should prepare for things like this in our quiz.
Yeah. It's going to take about an hour or two. So, so you
The one next week, sir.
Yeah, for next week. Yeah, for next week. So it's going to be engaging. So it's one of two things. It's either we set up breakout sessions where you guys will be interacting in your groups and then achieving your project, or we just restrict the activities to LMS, then while you guys interact to come up with your report. But you definitely come up with a report, which you submit to LMS. You upload it to LMS within the time frame. So once the time elapsed, then you may not be able to submit. So you want to work within the time. Okay, so you have about 2 hours, then you want to work within 2 hours to achieve your, something like that. So it's going to be engaging. We are going to be having our class. So it's not going to be time for you to relax, but it's just to get your hands a little dirty on the job. Okay?
Yes, sir.
Okay.
Sir,
Alright,
what
sir.
if we have like problems uploading it, like
I don't
uploading
think,
to the LMS?
well, I don't think you have problems uploading it. So you work with about half an hour or half the time duration. So if you have 2 hours, try to execute your activities in 1 hour. So within another hour, you should be able to submit for 30 minutes. But if you run into issues at that instant of time, then let me know.
Okay, sir.
Okay, so so we don't want to get feedback after the class activities. Okay, so we don't want someone coming a minute after the class to say, well, I could not submit. So let us know, just give us feedback either through text messaging or whatsoever while you're still in class, so we know, okay, fine, you're running into issues, then we could probably let's say provide an alternative measure at that point in time. So everything is going to be timed really. Is that okay?
Yes, sir.
Yeah, so anything outside the time, then we don't want to attend to that, okay? So, okay, that's fine. So group 2 would love you to share your screen. So for your presentation, for your in-class presentation.
Okay, so good morning, everyone.
Good morning.
I'm Cordial Professor, and I'll be leading off the presentation for this week on sequential logic and finite state machines. So, next slide. So, what is sequential logic? It is a crucial concept in digital electronics where the output depends not only on the current circuit, but also on the history of the use. So, unlike conventional logic that depends only on the present inputs, it also relies on memory elements like flip-flops or latches to store past states. So, these memory components enable the circuit to retain information between clock cycles effectively while remembering past inputs. And it achieves synchronization using clock signals, which provide regular pulses to ensure that all parts of the circuit update their state in unison. So it makes sure that it's used to make sure that clock signals are used to make sure that the input signals that they are updating their states at the same time, so that one is not lagging behind the other. So this capability makes sequential logic essential for devices that process data over time, such as counters, registers, finite state machines. And this forms the backbone of complex digital systems. Types of sequential logic. We have the synchronous sequential logic and asynchronous sequential logic. So for the synchronous sequential logic, in synchronous circuits, changes in the state occur in sync with the clock signal. So it requires the clock signal for it to work, or for it to reflect its changes. So All memories, all flip-flops or memory elements are triggered by the clock, ensuring that the circuit's behavior is predictable and reliable. Examples include flip-flops. So, like we said in class, we have the D flip-flop, the JK flip-flop, the T flip-flop, and the SR flip-flop. Then counters and shift registers, and it is used in microprocessors, synchronous state machines, and digital communication systems. Next slide. Asynchronous sequential logic. In a synchronous circuit, changes are driven. State changes are driven by changes in inputs rather than a clock. So these circuits are typically more faster but more complex to design because they require careful handling of timing issues. So they don't require it doesn't require a clock signal to work. So this makes it faster than the synchronous circuit because it changes based on the inputs that it receives. So examples of include asynchronous counters, other prone logic, checking circuits. They can faster than synchronous circuits as they don't wait for a clock signal, but they are more complex to design and they are prone to risk around conditions. Applications. It is used in high-speed digital systems, communication systems, and low-power designs. Key elements in sequential logic include the flip-flops. They are the basic building blocks of synchronous sequential logic. They store a single bit of data and they are edge triggered. The types which I mentioned earlier, again, the D flip-flop, the JK flip-flop, and the T flip-flop, and the SR flip-flop. So then we have latches. They are level-sensitive memory elements that store data based on the level, high or low, of the input signals. Then we have registers. They are a collection of flip-flops used to store multi-bit data. They are fundamental in data storage and transfer within CPUs and memory systems. Then counters. They are sequential circuits that increment or decrement a binary value. They are used for counting events, clock division, and generating timing sequences. Then we have state machines, e.g., the Moore and the Mealy machines. They are used to design complex sequential circuits. The transition between different states based on inputs and the current state. So the Moore machine depends only on the current state, and the Mealy machine depends both on the current state and the current input. Next slide. Next slide. Okay, sorry. Finite state machine. A finite state machine is a mathematical model.
Just a moment, please. Are you the only person presenting in your group?
No, sir, but I was the one that worked on this.
Okay, go ahead, please. I just wanted to confirm.
Okay, sir. A finite state machine is a mathematical model of computation used to design both software and hardware systems. And the reason it is called finite is because it has a limited number of states. And it is called a state machine because its operation is defined by transition between different states based on the input and the current state. Can you hear me?
Can hear you. Go ahead, please.
Okay. So FSMs are widely used in digital systems.
Sorry, trust everyone in class can hear him.
Yes, sir.
Yes, sir.
Okay, go ahead, please.
Yes, sir.
And an FSM operates by having a set of states, a start state, a set of inputs, and a set of transitions between states. and it can be classified into two types: deterministic finite state machines and non-deterministic finite state machines. For deterministic finite state machines, is where each state and input, where for each state and input there is exactly one transition. While for the non-deterministic, for some state input pairs, there might be multiple possible transitions. Components of a finite state machine. We have the states. So distinct conditions a system can be in with only one active state at a time. For example, the red, yellow, or red, green, or yellow for a traffic light. The start state, the initial state when the FSM begins or resets. Transitions, the rule that defines how the FSM moves from one state to another based on input conditions. Then inputs, external signals or events that trigger state changes. For example, a button persisting, an elevator. Then outputs, actions triggered by a state or transition, e.g., displaying a message in a Mealy FSM. Then state diagrams, a visual representation of the FSM with states as circles or rectangles and transitions as arrows labeled with conditions. Next slide. Types of finite state machines. We have the Moore machine and the Mealy machine. In the Moore machine, outputs depends only on the current state and not on inputs. For example, a vending machine where dispensing items based on its state. For example, waiting for money. And the Mealy machine, output depends on both the current state and the input. For example, a subway turnstile where the output open or closed. It depends on both the states, whether it is locked or unlocked, and the input if a coin is inserted. Then it's represented either in a state transition table or a state diagram. The state transition table, it's a table that shows the current inputs and the next states or outputs for Mealy machines. But the state diagram, again, is a graphical representation with states as circles and transitions as arrows labeled with inputs and outputs. Next slide. So, the working principle of an FSM. So, we have the start where the FSM begins in the initial state when powered on or reset. Then the input, it receives an input signal deciding whether a state transition would occur. Then we have the state transition based on the current state and input. The FSM moves to the next state. Then we have the output. Some FSMs produce output based on the current state more or both state and input really. Then you repeat the entire process. Applications of FSM, it is used in digital circuit design, control systems, networking protocols, and software systems. Its advantages, it is very predictable, it is simple, it is efficient, it is flexible, and then its advantages, it has something called state explosion, where large systems can result in complex and hard to manage diagrams, and it is limited. And it is limited. So I'll pass on to the next person to present now.
So good morning, everyone. Can you hear me?
Yes, we
Yes,
can
we
hear
can
you.
hear
Go
Morning,
ahead.
Miriam. We can hear you.
Okay, so I'm going to continue from where it stopped, and I'm going to be talking about the optimization techniques for FSMs. So FSM involves optimizing a finite state machine involves identifying the version with the fewest possible states while maintaining the same functionality. And the fastest method for achieving this is the Upcroft minimization algorithm. And also we have other approaches that include utilizing an implication table or applying the Moore reduction procedure. For acyclic finite state automata, FSs, minimization can be performed in linear time. The Upcroft minimization algorithm, this is the highly efficient method used for minimizing deterministic finite automata, and it reduces a DFA to its smallest equivalent form by identifying and merging indistinguishable states, ensuring that the minimized automation preserves the same language. The algorithm is particularly notable for its complexity, time complexity, making it one of the fastest methods for state minimization. The core principle of how it works is it employs partition refinement. This means the states of the operation are divided into equivalence classes based on their behaviors. So these classes are refined iteratively by examining transitions under input symbols, grouping states that exhibit the same response to inputs. Next slide, please. Next slide. So the applications of Upcroft's algorithm is that it is commonly used in areas like compiler optimization, formal language processing, digital circuit design, where reducing the number of states can significantly improve performance. And the major advantage compared to other methods like Moore's algorithm, Upcroft is more efficient and ensures a unique minimized DFA. It is especially suited for large automata with numerous states. And like I said earlier, other approaches are utilizing an implication table. So this means the implication table is a rigorous method used to minimize states in a finite state machine by determining which states are equivalent. The steps in this method, firstly, we construct the table. That is, create a triangular table where each cell corresponds to a pair of states. The table systematically compares states to check for equivalence. Then we mark distinguishable pairs. For each pairs of states, compare their outputs for every possible input. That is, if output differs, the states are marked as distinguishable. Then iterative refinement. For states with matching outputs, examine transitions to their next states. Next slide, please. If transition leads to distinguishable states, then the current pair is also marked as distinguishable. Then the last part is merge equivalent states. So any unmarked pairs, that is the one that are indistinguishable, they are merged into a single state. And the advantages are it guarantees accuracy in identifying equivalent states, and particularly effective for small to medium-sized FSMs. Some major challenges, like one of the major challenges, preparing and filling the table can be tedious and computationally expensive for large FSMs with numerous states. Then the second method I talked about here, the Moore reduction procedure. This is another widely used method for FSM minimization, emphasizing grouping states with similar behaviors. The steps in this procedure: first, initial partition. We group all states based on their output, that is, states producing the same output are grouped together. Then refinement, check the transition of each state in a group. So if two states transition to different groups for any input, they're separated into distinct groups. Next slide, please. So after refinement, we repeat until convergence. That is, continue refining the groups until no further splitting occurs. The final group represents the minimized state of the FSM. Then lastly, we construct the minimized FSM, create a new state for each group, and define transition based on the original FSMs. The advantage of this is it is easy to implement for deterministic FSMs, and it guarantees the minimum number of states with well-defined steps. Major applications commonly used in digital circuit design and optimization. Then it is useful in simplifying control logic for hardware and software. The key differences between these two methods is that implication table focuses on pairwise comparison of states, while Moore's method involves grouping and refining based on behavior. And the implication table is more suited for explicit checking of state equivalence, whereas Moore's method provides a more abstract grouping-based approach. I'll pass it to the next person. Thank you.
Okay, good morning everyone. So I'll be continuing from where she stopped. I'm talking about FSM decomposition methods. So firstly, what is FSM? FSM are finite state machines. What is the FSM decomposition? FSM decomposition refers to the technique used to break a complex FSM into a smaller, simpler FSM that works together to achieve the same overall behavior. This composition, it helps improve the modularity, the scalability, and the ease of design So there are a lot of several methods of which I'll be mentioning few of them. There are several methods used in FSM decomposition. One of it is FSM partitioning. This method include dividing the state. It includes dividing the state space of the original FSM into smaller, non-overlapping partitions. Each of these partitions forms a separate FSM, and this smaller FSM interacts to produce the overall behavior. Example of state partitioning FSM include a traffic light controller. A traffic light controller can be partitioned into smaller state FSM. So each FSM will be handling the state of the FSM, each sub FSM. So there will be one handling the state, like for the green light, one for the yellow light, and another for the red light. Then moving on, another method of the composition of FSM that we have functional decomposition. So the functional decomposition, the FSM is divided based on functional aspects or tasks. Each sub FSM is responsible for a specific function. In the case of space partitioning, each division is not really responsible for a function per se, but it is responsible for like a state. Just like a state, we have a green light now, and our traffic light. A green light is a state, that is like a state. Then yellow light is a state. But in functional decomposition, so each FSM take a task, so perform a function. So each sub FSM is responsible for a specific function in this state. Example of a functional decomposition is a communication protocol. In a communication protocol, one FSM might handle data transmission while another handles error correction. Then moving on, we also have the sequential decomposition. For this sequential decomposition, so the division into smaller FSM is based on sequential stage of operation. So each sub FSM represents a stage, and the output of one FSM acts as the input for the next. So it's just like a stage-like type of decomposition. An example of this type of decomposition is a pipeline FSM in a CPU. Where each stage handles fetch, decode, and execution, like fetching, decoding, and execution. So this operation now in a CPU, it is a sequential decomposition type of execution. Next slide, please.
Hi everyone. I'll be presenting Moore and Mealy machines. So Moore and Mealy machines are the major types of finite state machines, and the difference between them is basically how they respond to an input signal. So Moore state machines are finite state machines whose output depends only on the present state of the FSM. And that means that in a Moore state machine, the output of the FSM depends completely on the states of the flip-flops or whatever memory logic circuit is used. modulo n counter. So as we know, a modulo n counter is a logical circuit that uses flip-flops to count from 0 to n. So n could be any integer basically in binary. So the output of the counter, as we know, depends only on the current state we are in. So if, for example, let's say we have a modulo 26 counter and we are on number 16, the next output in the sequence depends only on the current number we are in, which will be 17. So as you can see in the circuit, the Moore machine is made up of a combinatorial logic that passes to the flip-flop, which is the memory state, and an output decoder. The purpose of the output decoder is to check if we are at the end of the sequence. So for example, in a modulo 26 counter, we want to know that if we are 26, the sequence should reset. Next slide. So Mealy state machines. A Mealy state machine is a finite state machine whose output depends not just on the current state of its flip-flops, but also on an input signal. So as you can see, the combinatorial logic in this case takes an input signal, and the memory or like the flip-flops in the circuits also play a part in determining the output of the finite state machine. Next slide. Next slide, please. So yeah, if we wanted to extend the previous modulo 25 counter I just showed, let's say we wanted it to be able to count to 25, 30, or 50, we would add like a select input decoder that determines if the counter should reset at 25 or 30 or 60. So in this case, we now have a finite state machine that has inputs that controls the output. So for example, unlike the previous Moore machine, when the counter gets to 25, for example, if the select input is set on 50, the counter would not reset and would continue counting until it gets to 50. And the same applies for counting to 100 or 60, or any number we decide for our select lines. Next slide. So also a key thing we should remember is that in finite state machines, clock signals are not considered input signals because they only serve the purpose of synchronization. So while both Moore and Mealy machines can have timing and clock signals, they are not considered inputs. So comparing Moore and Mealy machines, in timing, in Moore machines, outputs only change when the state changes, and like basically they're synchronous. While in Mealy machines, outputs can change at any point in time whenever the input changes. And then comparing speed, Moore machines have a slower response to the input since output changes after state transitions, just like I just said. And then in Mealy machines, outputs can be instantaneous and can change with input. Next slide. So complexity. More machines require more states to achieve the same behavior that you get for any output because they don't rely on any input. So you basically have to have as many states as the number of combinations you're trying to model. While in Mealy machines, you can have select inputs that cut down the amount of states you have to model. Like for example, in the counter I just showed, if we were going to model the counter to count to 100, we would have to have as many states as like basically 100 numbers. While for a Mealy machine, we could just set a select input that determines whether we're counting to 25 or to 100 using the same basic number of flip-flops. And then for output stability, Moore machines tend to be more stable since we can only change between state transitions, and while Mealy machines can have unstable outputs. For example, in JK flip-flops we explored earlier in class, we saw how there's the possibility of invalid states, basically, because the inputs and the outputs can change at the same time. It is almost impossible to predict what the next output in the logic circuit would be. Next slide. So transition rules. Basically, there are rules for how we can transition between states in a finite state machines, and they're fundamental. When you're transitioning from a state to another, the first rule is the sum rule. the Boolean sum of all your state conditions must always be equal to 1. That basically means that if, for example, in a counter, when you're going from a number to another, the only state condition you have in that point is just the current number you are. And that's not really a good example. Well, if we had a Mealy machine, for example, like the one in this picture, we have three transition variables, and the Boolean sum of all three transition variables must basically always be equal to 1. And then the mutual exclusion rule, which says that each transition condition cannot be associated with any other transition path. That basically means that if you're at any state, there should be only one condition that moves it to another state. So two transitions cannot share the same condition, because then that would just confuse a state transition basically. So next slide.
Okay, we have just 5 minutes to wrap up your presentation, the entire presentation. So you want to speed up your process, okay?
Okay. So designing finite state machines, there are basic steps for designing a finite state machine. 1, you derive the state diagram, you draw up the state table, you assign bit combinations to the variables in order to represent the different states and drop the corresponding state table. You choose the flip-flop type, you derive the input equations based on corner maps from the table, and then you represent the resulting logical circuit. Next slide. So as an example, I used a JK flip-flop as a finite state machine. So yeah, the state conditions are the current input or the current values J and K are holding, and your outputs are the Q and Q bar outputs, which are basically the current bits you're trying to set and the next bits. So from your, sorry, can you go back to the previous slide? Yeah. From your state diagram, you can assign various the bit combinations for each state condition. So that is left to the situation you're trying to model with the finite state machine. And yeah, moving to the next page. So deriving an input from your state diagram, then from your state table, sorry, you can then apply corner maps and grouping adjacent ones and to derive a simplified form of your output, which in this case is the next state of the JK flip-flop, as we've seen earlier. And then from your output equation, you can draw your logical circuits. So looking at the JK flip-flop, it is tempting to classify it as a Mealy model, since its output depends on the variables J and K. But then it's important to remember that J and K only determine the next output in the flip-flop, since we're trying to remember what our current bit is or whether we're trying to reset our current bits. So therefore, a JK flip-flop is a Moore machine. Moving to the next slide. So real-world examples of Moore and Mealy machines. A traffic light controller. A traffic light controller has 3 outputs: red, green, and yellow. And its inputs are a pedestrian button that's trying to cross, for example. So a traffic light is a Moore model because, like I said earlier, its inputs only affects the transition. So when a pedestrian is trying to cross the road, even if they click on hit the pedestrian button, they can only influence the next state of the traffic lights. They can't change it from red to green or yellow at that point. And then network protocol handshakes. For example, in TCP and TLS connections in HTTP protocols on the internet, it can be modeled as a Mealy machine because the current output of the handshake, which is basically the two devices acknowledging that they have both made a connection, depends on both the current state of where they are in the handshake and their previous handshake steps. And then lift door with safety sensors and keypad activated door lock. So yeah, next person.
Yeah, good morning. So let me just round up. So introduction to FPGA final system design and implementation. Involves creating hardware-based state machine using field programmable gate arrays. This approach is widely used in digital design for applications requiring high performance, real-time control, and flexibility. We know that our final state machine is a computational model used to design system with finite number of states and transition. FSM can be represented with some characteristics. So we talk about the state, which define the current condition of the system. The transitions describe how the system moves from one state to another based on inputs. And then we know our input, which are external signal, any form of signal that influence transitions. Then our output signal, which is generated based on the current state and the input. So like we all know that our FSM can be classified to more FSM, which is the class A, and Mealy FSM, the class B, which output depend on the current state and input. So why do we use FPGA for FSM? FPGA are the configurable device ideal for implementing FSM due to parallel processing. You know, FPGA can handle multiple FSM concurrently, low latency, hardware level implementation, ensure real-time response. Then flexibility, FPGA can be reprogrammed to accommodate changes. Then we'll talk about the scalability suitable for small FSM to complex state machine with numerous states. There are steps in FPGA-based FSM design and implementation. Number one, we talk about the specification. Therefore, we design the problem, state transition inputs and outputs, as earlier mentioned. Then we have a state diagram. We draw a visualized representation for the FSM to organize transitions and outputs. Then we talk about the state encoding, whereby we put to the process whereby we assign binary codes to each state for hardware implementation. Therefore, we talk about the hardware description language, which is the HDL, Verilog, and the VHDL, which we've seen in class. So use processes or always block to describe transitions outputs. Then number 5, we synthesize and simulate. Synthesize the HDL code into a netlist capable, compatible with FPGAs. Then we simulate the design to verify the functionality. Implementation of FPGA. We use FPGA tools like Intel, Quartus, and the Xilinx Vivado to map, place, and route the design. Also, we can program the FPGA. Then testing, validate the FSM on hardware using test benches or external inputs. Advantages of FPGA-based FSM design. Number 1 is high performance with real-time responsiveness, reconfiguration for iterative development, suitable for complex systems with high reliability. So those are the advantage. And the challenge: efficient state encoding to minimize resource usage, debugging and verification at the hardware level, balancing power, speed, and resource utilization. So by mastering FSM design on FPGA, engineers can build efficient control system for robust communication protocol, embedded system, much more. So that was all.
Okay, nice presentation. Unfortunately, we do not have much time to entertain questions. Well, we'll try to pull the questions over to next week. We'll be having a class quiz. And it's quite interesting that you talked about the feed programmable gate arrays, the FPGAs. So meaning you could be assessed next week to develop some kind of reconfigurable devices, okay? Where you have to probably play with FPGAs, or better still, the program or the model, or better still the code in VHDL or Verilog. So you want to get prepared. So all we've done so far should be sufficient to guide our application, okay? So I think we'll call it a day for now, since we'll be getting into another class in a minute. So bye for now.
Thank you, sir.